So welcome back. This is the fourth lecture on a series of lectures called Solving Nonlinear Equations with Linear Algebra. On the first lecture, we established the classical background for solving nonlinear equations. Then on the second and third lecture, we did the connection with linear algebra. And today we're going to talk about the complexity of these algorithms and the relation with the module of syzygies. If you haven't watched the other ones, they are going to be recorded. They are going to be available online. And before I start, I'm going to try to make the slides available. And at the end of the third set of slides, there are some additional references that are not the first reference for some topics, but they are very useful. These are the book by Cox, Little, of Shia of Ideals, Varieties, and Algorithms. Then my master thesis is about the F4 algorithm. And so these additional references give you more insight in some of these topics. Then there is my PhD dissertation, which is about computation of Groebner bases and mutant polynomials. Then there's the PhD dissertation of Martin Albrecht about algorithmic algebraic techniques and their applications to block cipher cryptanalysis. And the thesis by Spalenhauer, resolution of systems. These are very good references to go and get more details about some of the topics we have discussed here. And I used them to prepare the lecture, this course. All right. Now, let me recap a little bit what we did last time. So, we were working on avoiding zero reductions. So when we do these algorithms to compute Groebner bases, we have many polynomials that reduce to zero. And in terms of computation, we want to avoid them. So we defined what it was. We discussed what the module of syzygies is and how it was important and what role it played, because the S polynomials can be thought of as a basis for the module of syzygies of the leading terms of the polynomials. And a Groebner basis can be characterized yes, a Groebner basis can be characterized by saying that all the if you have any basis, not only the S polynomials, but any basis for the module of syzygies is enough to characterize what a Groebner basis is. We want a basis for the module of syzygies, and if every element in that module of syzygies goes to zero, using this set of polynomials, then we have a Groebner basis. Now, that allows us so that gives us the idea that we can simply use a smaller basis for the module of syzygies, and that will speed up the process of computing Groebner basis. So we have some criteria for removing elements in this module of syzygies that are redundant. This was one of those. And it's a bit technical. It has some condition on the leading terms, But the good thing is it allows us to remove some of these CCGs of the leading terms and still have a basis for the module of CCGs of the leading terms. And so, just to wrap up this part, what we want is a systematic way of using these criteria to remove elements from the module of CCG, from the basis of the module of CCGs, and still have a basis. And I'm going to show you how this is done in the Buchberger algorithm, right? So in the case of the Buchberger algorithm, instead of taking every element from the basis f, from the original set of polynomials, and every S polynomial and every pair, what we're going to do is we're going to have an update function. This update function is going to insert elements f one at a time into the basis G, and it's going to form pairs. And it's going to make sure that it avoids redundant pairs. Pairs that we know are redundant for the module CCGs that are linearly dependent. And it's going to do that at the beginning, and then it's going to do that again when we get non-zero remainders, right? It's going to do it at the beginning and also every time we find a new element for the basis of polynomials. Now, how does the update function look like? It's complicated. It's a systematic way of checking those conditions and avoid some CCGs, some S polynomials that we know are redundant. And we see the criteria somehow hidden there. You have to go through it carefully, but the idea is that we are removing some pairs if they satisfy certain conditions. We remove here, and we remove here. And what are the conditions? Well, for example, if the leading monomial of H and the leading monomial of G are disjoint, we can remove that pair. We know that one is redundant. That one is going to reduce to 0. That was the first criterion we talked about. And then there's another criterion here. There's another, for example, here, if the leading monomial of H, the least common multiple of the leading monomial of H and the leading monomial of G2 divides the least common multiple of the leading monomial of H and the leading monomial of G1, then we can remove this. So I know it's complicated, and the point is not to understand every single line here, but the idea is you have this criterion and you systematically reduce the size of the basis of the module of CCGs of the leading terms of your polynomials, so that you don't have to check, you don't have to then consider so many pairs. All right. Any questions from the audience at this point? Okay, then let's move on. You can do exactly the same on the F4 algorithm. And that was the nice thing about the F4 algorithm. It's based also on pairs. So you can do exactly the same on that you do with the Buchberger algorithm. You do update here, you do update here, and so you avoid redundant pairs. Now, it is much harder, or it is not so clear how to do it if we have something that like the Excel algorithm. I'm going to recap what the Excel algorithm is so that we are on the same page. Okay, so let's remember the idea, at least, of the Excel algorithm. So we were trying to solve a system of polynomial equations. And what we did was we take these three equations. This is what we want to solve. We linearize, put them into a matrix. We do Gaussian elimination. We are not able to solve yet. So what we do is we expand by multiplying by variables to get more polynomials. As we get more polynomials, we get these 6 new polynomials. We put them in a big matrix together with the original 3 ones, and then we row reduce that matrix. And hopefully at some point, we will get a solution to the system or a Groebner basis. In this case, we get 2 linear equations at the end. They correspond to linear equations in the 2 variables. We get the unique solution of this system. And the question here is, well, there are going to be redundant rows, right? There are going to be how to avoid them. This is as we go up in degree and we increase and increase, there's going to be rows that reduce to 0. And if we can avoid them before we construct this huge matrix, that would be great, because there's going to be a lot of redundant rows. So the more we can reduce that, the better. And that's what the F5 algorithm does. It provides us with a systematic way to avoid lines in this sort of algorithm. I'm going to present it in the matrix version. Here we go. So, given a set of polynomials, actually an n tuple of polynomials f1 through fm. So each row of the Macaulay matrix TFI is labeled with a signature. So we are defining a signature for each row. The signature gives us the monomial T we're multiplied by, and the position corresponding to the original polynomials, right? Now, we want to keep the labels through the Gaussian elimination process. We don't want to lose the labels, even though we are doing reductions, row reductions on the matrix. And to be able to do that, we need to make sure that we reduce only downwards during Gaussian elimination. And we do not switch rows. Is that possible? Yes, we can do Gaussian elimination. We are not going to get row reduced echelon form, just an echelon form. And it's not going to be ordered, but we can do it. So I'll give you a quick example just so that you convince yourselves that this is possible. Let's say that at some point on the Gaussian elimination, you have a pivot at this position. You clean the column, you put zeros down from there. And let's suppose that when you jump to the next column, you want to find a pivot in the next row, but there was a 0, just by chance, right? So I don't care. I don't mind. It's not a problem. I'm not going to switch columns. I'm not going to do that. I'm simply going to use the first non-zero entry of that row, and I'm going to clear the column from there downwards, right? And then hopefully at some point there will be another pivot down that column. Could be, maybe not, it doesn't matter. But the important thing is that we're only reducing downwards, which is important because it guarantees that this row, let's say, yes, this row is a linear combination of the previous rows. Always, even though we're doing all these things, we always guarantee that one row is a linear combination of the previous, of the original ones up to that one. Of the original ones up to that one. So, yes. And this assures that we keep an order among the signatures. So we should establish an order in the signatures. This is like an order. Yes. So position first and a monomial later. So this allows us to talk about an order in the signatures. So for example, let's say S if I is less than T if J if S. Sorry, let's do position first. So when I'm talking about position, is the position in the CCG. So it's if I is less than J or I is equal to J and S is less than T. Position first, and then the order by the order of the monomials, the order in the ring. So, why is this important? So the first criterion we're going to have is just to have a systematic way of creating the new rows from the previous degree, right? So given an echelon form, M tilde of the Macaulay matrix at degree D, we're going to use the non-zero rows of M tilde to construct the next degree Macaulay matrix. And we're going to do it avoiding repetitions. So what this is going to give us is if at some point we find a zero reduction, we're not going to use it again. It's a zero row. We don't multiply that one by anything, right? We only use non-zero rows. So if we already found a CCG, we're going to avoid it from there on. But we have to do it avoiding repetitions. So I'll give a quick example here of what I mean. So let's suppose we have a signature here, let's say S Fi, which corresponds to some row in the Macaulay matrix. Right, and then we have, so let's be specific here. Let's say this is just 1 times Fi, right? So this is just the original Fi. Let's say it's a quadratic polynomial, right? So we are at degree 2, right? And we also have 1 Fj. This is another row in the Macaulay matrix. So we're going to construct the next polynomials at the next degree by multiplying these ones, right? We do Gaussian elimination here. So this may become something like this. This one, let's say, is something like this. So we have a 0 here, and it got reduced. Now, we use the reductions we already did. We construct the next degree Macaulay matrix from this one by multiplying by variables. So we're going to take this one here, and we're going to multiply it, I don't know, by x, right? So we get a new one with a signature x and I. The next degree. We do the same with the other ones, right? And that's what I mean by constructing the next degree from the previous one. Multiply what we already have by the next one. Well, let me put another one here. Let's say x fi multiplying by y. Now, when I say avoid repetitions, what I mean is you have to be careful that when you go to the next degree, you don't do the same thing twice, right? So if we multiply this one by y, we get x, y, and I. And clearly, we don't want to multiply this one by x because we're going to get the same thing, right? So just we need a systematic way of doing this. Avoid the repetitions, use the Macaulay matrix, echelonize to construct the next one. That's called the rewritten criterion of F5. Nothing very special, but it's important to have it in place. I mean, this one is important in this following sense. So this is not going to avoid. So if you find at some point a zero row, you don't multiply it anymore. So it's like you found a CCG. So you already have it, and you avoid anything that comes from that already. So it allows you to use the information you get through the process of constructing this Macaulay matrix. Now the next one goes in a different direction. The idea now is we know there are some trivial CCGs, and we want to avoid those. Explain the idea first before I keep the criteria. So in that process, we know that Fi, Fj minus Fj, Fi is equal to 0. So this is true for any f for any I and any j, I different from j. And this is going to cause a lot of redundancy on these Macaulay matrices. So we want to avoid this. If we can remove something so that we avoid those zero reductions, it would be great. Now, I want to look at this not in terms of Fi and Fj, but in terms of the monomial multiplied by the polynomial. So let's write Fi. Let's suppose that Fi is of this form. A sub t yeah. So some coefficient here is t in some set of monomials. Let's say I don't know, of degree d minus di or something. So I'm saying here that yeah, this I will talk about this later. But let's say this fi is some polynomial at times t, the sum for some monomials, some set of monomials, and we're multiplying by fj, and then we are subtracting the sum of fj. Now fj, let's write it as b sub t, t, fi, and let's say we're on the same set of monomials. Now here it is. D ice. So that relation leads to a relation among the rows of the Macaulay matrix. Each of these things here corresponds to a row in the Macaulay matrix. And what we want is a systematic criterion to remove one of those from the Macaulay matrix. And that's exactly what the F5 criterion does. So first, some notation. I'm gonna call MDI of F, the Macaulay matrix on the first I polynomials of degree D. So for simplicity, let's think that the polynomials in F are homogeneous. And yes, we consider the Macaulay matrix of the polynomials up to the ith polynomial, and we do it at degree D. This is what the F5 criterion says. It says, for all j less than m, if we have a row labeled tfj in the echelon form of md minus dm m minus 1 that has leading term t prime, then the row t prime of m in MDM is redundant. So it's like we're picking one of these and we are saying that one is the one we're going to remove. Which one? Well, that's what this says. It's a systematic way of doing it. Now, notice that here we're talking about a Macaulay matrix at a lower degree, D minus dm. Here, dm denotes the degree of the mth polynomial. D prime is the leading term of that row. So we have a row labeled tfj that has a leading term t prime. And then what we're saying is we don't have to do the row t prime of m at degree D, capital D. Let's prove that that's true. Let's suppose F is an element So I'm going to abuse notation here. I'm going to say this is an element in the Macaulay matrix. What I'm saying is take a row considered as a polynomial in the Macaulay matrix, right? So in d minus dm, comma, m minus 1. It's going to be f. Such that the leading monomial is t prime. That's the one we're going to avoid, right? And with signature, in this case, the signature is TFJ, right? TFJ. And what we want to show, that the row corresponding to T prime Fm is a linear combination of previous rows. The row corresponding to T prime Fm is a linear combination of rows above and because of the ordering on the signatures, this corresponds to a linear combination of rows with a lower signature. That's exactly why we have this ordering on the signatures. Okay. So let's suppose that so we know that F is the sum of some HI I, where I is less than M. And what do we know about these HIs? Yes, let's say of degree less than D minus dm, right? These HIs are polynomials. All right, then let's put that here. What is critical here is that because F is in this matrix, in this Macaulay matrix, then it is constructed out of the polynomials Fi with I less than M. That's what is going to be important here. And now, let's see what happens with T prime Fm, which is the one we want. Let's try to write this one as a linear combination of the previous ones. Right. Now T prime is the leading monomial of F. Now the leading monomial, I like to write it as F minus the rest of F. So F minus, let me call this F underbar. So what I mean here is that F underbar is precisely the rest of F. So it's F without its leading term. So the important thing here, sorry, this is F underbar. F underbar is what is left when I remove the leading term. And what is important here is that the leading term of F underbar is strictly less than the leading monomial of F, of course. Now, let's split this into the two parts. So we're going to get F times Fm, but F is this. So we get I less than M, and then we get the H sub i's. Let me leave the Fi at the end. So Hi F Fi. Then minus F underbar Fm. Okay. And it should be now, the result should be more or less obvious now. Now, here on this side, we have i's that are less than M. So they have a lower signature because they are using polynomials that are before M. So here we're getting signatures with I less than M. So they must be above T prime Fm. And here, if we expand F underbar, well, all the terms, all the monomials that appear there are less than T prime. Here we get signatures. I ran out of letters. S, F, M. In this case, we got the same M, but we have S strictly less than T prime. In both cases, we're talking about rows that are above the row of T prime Fm. So with this, we have so this finishes the proof. And we have established this F5 criteria that allows us to remove redundant rows that come from the trivial syzygies. Now, I'm gonna leave it there for now. Yeah, I'm gonna leave it there. So we can write an algorithm based on this idea, remove redundant rows using the rewritten criteria and this F5 criterion on the F5 algorithm, on the Excel algorithm. And what is really impressive and it's really interesting is not only that you can remove some of them, but you can remove all of them. And under certain conditions of regularity, you have full rank Macaulay matrices. You're going to have no zero reductions. I'm not going to prove that here. There's not enough time, but it's possible to prove it. Are there any questions? The people in Zoom, questions? All right. So since I'm gonna now change topics, I'm gonna take the chance to take a break now. For 10 minutes, it's 3:44, and we can get back at 3:54, 3:55, let's say. 10-minute break. And when we come back, we're going to talk about the solving degree, which has to do with, and we're going to find a way, we're going to talk about a way to, for certain systems that are regular, that have only these kinds of trivial syzygies, we're going to show that we can predict exactly how many rows we're going to have, up to what degree you have to go. We know everything about those. All right, so I'll see you back at 3:55 in exactly 10 minutes. So in the hour that I have left, I'm going to be talking about the solving degree, and I'll talk a little bit about matrix reduction algorithms. There's a lot of information here. I know this has covered many topics, so I'm going to be moving a little bit fast here on this theory, and you can always go to the references, and also I'll be happy to answer by email and help you out if you have further questions. Okay, so the solving degree, what we mean by the solving degree is if we consider these algorithms that start with the Macaulay matrix, expand to a larger degree, and then keep expanding, what is the degree at which we solve the system? That's what we call, loosely speaking, the solving degree. Of course, the solving degree is going to depend on the specific algorithm, but we can try to restrict ourselves to a simple case. So that, yes, so we can actually point to something. So let's talk about an Excel algorithm. Let's suppose we are using homogeneous polynomials. So on this part, I'm going to be talking only about homogeneous polynomials. Just the simpler case, it gets a little bit more complicated if we talk about something like F4, or if we talk about non-homogeneous polynomials, if we include mutant. Now, it's going to change a little bit, but for simplicity, let's suppose the polynomials are homogeneous and we're doing Excel. Right. Now, one thing that is very important in this discussion is the Hilbert function. So the Hilbert function of this quotient, this is the polynomial ring over the ideal, is defined, is a function from the non-zero integers to the non-zero integers, and is defined as the Hilbert function of degree D is the dimension of that quotient at degree D. And by that, we mean, and that's what it is. Now, these are, if you remember, these are vector spaces. So we can talk about the dimension. And we can think, if we want an intuition, so this part here, the polynomial ring at degree D, its dimension is the number of monomials at that degree. That's it, that's the dimension of that degree, the number of different possible monomials. And then the dimension of ID is, of our ideal at degree D, is the number of leading monomials on the, that can be obtained, the leading monomials in the ideal. And that's why this quantity is so important, because it tells us how many, like the difference between the total number of monomials at that degree and the number of leading monomials in our ideal. Now, we often use the Hilbert series, which is just the power series where the coefficients are the Hilbert functions at the different degrees D's. This is just a formal series. It's a way to have all the Hilbert, the evaluation of all the Hilbert functions in a nice, simple, compact form. But this is not adding anything new. It's just, in a way, notation. And it helps us because we know how to manipulate the power series. So that's often very nice. But what is important here is the coefficients, which are the Hilbert functions, which tells the dimension of the quotient at degree D. And here's the thing. There's an important theorem that says that there exists a degree D, such that for every degree larger or equal to D, the Hilbert function is a polynomial in D. So it's saying that starting at some degree, the growth of the Hilbert function is stable. And this is precisely when we reach Groebner basis. When we reach a Groebner basis, we have all the leading monomials, and everything you get from there, you get it simply by multiplying the leading monomials by variables or by monomials. So we know exactly how it grows from that point. Once we get to a Groebner basis, we know exactly how it's going to grow. We know that from that point on, it behaves as a monomial ideal. That's the key here. It behaves as a monomial ideal. And the smallest such degree D is called the index of regularity. And the index of regularity is the largest degree of any polynomial in a reduced Groebner basis of the ideal. That's why this idea of the Hilbert function is so important, because it gives us the degree, largest degree of any polynomial in the Groebner basis of idea of a reduced. So this is for a homogeneous set of polynomials. It tells us precisely up to what degree we have to go to compute the Groebner basis. So one way to understand the complexity would be to know the index of regularity. However, the only way we know how to compute the index of regularity is to find the Groebner basis. So that's not very good, except that there are some systems for which we do know how to predict the index of regularity. And here is such a case. I'm gonna define what a regular sequence is. And for regular sequences, we know very precisely how it behaves, so we can predict the index of regularity. So I'm gonna define a regular sequence as follows. A sequence F1 through Fm of non-zero homogeneous polynomial is called regular if for I equals to 2 to m, 2 up to m, and every element in the polynomial ring, GFI belongs to the ideal generated by F1 through Fi minus 1, implies that G belongs to that idea. In other words, Fi is not a zero divisor in this quotient. So the next polynomial is not a zero divisor in the quotient of the ring over the ideal generated by the previous polynomials. It's not obvious at all why this is important, except that F is regular if and only if the modulo of syzygies of F is generated by the trivial syzygies. These ones up here. Those syzygies are always there. And there are systems for which these ones are the only ones. Those are the regular sequences. And thus, if we can remove the regular, if we can remove the trivial syzygies, if we can avoid the reductions that come from trivial syzygies, then we're going to remove every single reduction to zero on a regular sequence. Okay, and we know a lot more than that about the regular sequences. So if it's regular if and only if the following is a short exact sequence. So this map here is multiplication by Fi, and this one here is the natural projection when we add one more polynomial on the quotient. So here what I mean by Pi is the ideal generated by F1 up to Fi. And so this is and R is the polynomial ring. So this is just the quotient at degree d minus di. This is multiplication by Fi, the quotient, the same quotient, but at degree d. And then the projection, adding one more polynomial to the ideal in the denominator. And it's actually not hard to see that this is a short exact sequence. The projection is clearly surjective, so is clearly onto. Multiplication by Fi clearly maps this ring here to the kernel of the projection, which are the elements generated by Fi, right? And then the injectivity of this map is given precisely by the condition that defines the regularity, right? Let's go back for a second. We said that is regular if Fi is not a zero divisor here. Well, if Fi is not a zero divisor here, then multiplication by Fi is injected. So once we have that this is a short exact sequence, then we know that the dimension of this here minus the dimension of this plus the dimension of this is 0. And so that gives us a recurrence relation among the Hilbert functions of these things for every I and for every t. Once we have that recurrence relation, we can compute the Hilbert function. And even better, we can get the Hilbert series. So this is a very good power series exercise. Once you have that recurrence relation, we can get this power series from there. Once we have the Hilbert series, we know everything about it. We also know the index of regularity. So index of regularity is exactly the sum of the di's minus m plus 1. Here, the di's are the degrees of the polynomials. So degrees of the polynomials, the degree of Fi is di. We know the index of regularity. Okay. Now, this only works for sequences where we have less equations than variables. Because if the number of equations is greater or equal to the number of variables, the degree, the dimension of the ideal is finite. And these cannot go forever. This condition cannot go forever. You eventually fill up completely the ring. Like you get to a degree where the dimension of the ideal is the same dimension of the ring. Now semi-regularity, semi-regular, the idea of semi-regular extends this notion of regularity when there are more equations than variables, or when the number of equation variables is equal. This is due to Bardet and others. Bardet, Faugere, Salpi, 2004. The reference is at the end of the slides. In that case, when we have more equations than variables, the ideal is zero-dimensional. Thus, the dimension of the quotient is finite. And then, in that case, the Hilbert series ends at some point. It's really not an infinite series, but it's a polynomial. We get to a point where it becomes zero, the coefficients are zero. As I said, at some degree, the dimension of the ring is equal to the dimension of the ideal. It fills completely the space. Okay? And so the way they deal with this issue is that they defined a sequence, they define a notion of deregularity. So regularity up to degree d. So let P be a sequence of homogeneous polynomials, d greater or equal to 0. We say that P is deregular if we have the same condition, but only for polynomials G such that GPI is less, that the degree of GPI is less than D. So we only require the condition of regularity to be true up to degree D. Right? Look, it's exactly the same condition. GPI belongs to Pi minus 1, and this condition implies G belongs to Pi. So again, G is not a zero divisor, but only up to degree D. And then with this, we define the degree of regularity of an ideal to be the minimum degree such that the dimension of the ideal at degree D is equal to the dimension of RD. And as the index of regularity, the degree of regularity is telling us up to what degree you're going to obtain a Groebner base for regular sequences. So a homogeneous sequence of polynomials is semi-regular if it is deregular, where D is the degree of regularity. Since when you have more equations than variables, it cannot be regular forever, we only ask it to be regular up to the degree of regularity. The degree of regularity is the dimensions of the ideal and the ring match. And that's precisely where you should get a Groebner basis for regular sequences. And then, again, we have everything. We know everything up to that degree. So P is semi-regular if and only if the Hilbert series is given by the same series, but this notation here, this plus here, means when this becomes negative, you just truncate the series to 0. So what happens is when m is larger than n, this series is going to start becoming negative at some point. Well, we only want positive coefficients. Those are the only ones meaningful, because the dimension of that quotient cannot be negative. It's going to be always positive. So when it gets negative, we truncate the series. We're just keep the first terms. And as with the regular sequences, for the semi-regular ones, P is semi-regular if and only if the ideal I has dimension 0 and every CCG of F of degree at most the degree of regularity is in the module generated by the trivial CCGs. So the same condition, but only up to the degree of regularity. Or in this case, the degree of the Hilbert series, because now the Hilbert series is a polynomial. Any questions? So there are other results in this area. For example, for the applications in cryptography that we do, we're often working on a small finite field like GF2. And we're looking for solutions of the system, not in the algebraic closure, but on the finite field itself. And in that case, we know there are other trivial relations beyond these ones. If the polynomials are homogeneous and we are over GF2, so we know that every element in the field satisfies that x squared equals x. And this imposes a condition on also, like it gives us a trivial CCG also on the polynomials. And so there are other CCGs beyond these trivial CCGs. And so we can do the same reasoning under some extra conditions. knowing that this happens and imposing this condition. And this is an ongoing effort, I would say. This is something of research interest to have more complicated systems with certain structure, but generic enough that we can know exactly the Hilbert series or the degree of regularity. This, for example, has been expanded to some things like HFE polynomials and also to bilinear polynomials, and for some sequences made of determinantal polynomials, it's also possible. So there's a lot of research going in the direction of characterizing some structure of some family of polynomials and trying to determine precisely the Hilbert series and therefore the degree of regularity, and so forth, knowing at what degree it is solved. Now, the degree of regularity works very well when we're talking about homogeneous sequences. But for non-homogeneous, it's a bit more complicated because you get these drops in degree. And there are examples. So the notion of regularity has been extended to non-homogeneous polynomials in two directions. One is homogenizing the polynomials, and the other one is only considering the largest degree part of the polynomials. And both have problems. They are not always accurate in what really happens. So there are other notions that are also useful. And also, the idea of calculating precisely the degree of regularity is not, or to estimate it, or characterizing this family is not always possible. So sometimes, for example, people have looked at the first full degree. This is another notion that is common in the literature of cryptography, the first full degree. And so I'm gonna quickly tell you what this is about because you may find it somewhere, some places. So here at top is the highest degree part of each polynomial. So we're looking at the homogeneous part of the largest degree. Then syzygies is the module of syzygies, and TRIV is the submodule generated by these ones and these ones. So this is precisely what happens when we assume that the largest degree part drops, disappears. Okay, and the first full degree can be defined as the minimum degree such that the quotient between syzygies and between the module of all the syzygies and the module of trivial syzygies is different from 0. So it's the first degree at which you get non-trivial syzygies. And it's often that I'm not even going to say a conjecture because it's not true in general. It's this notion of first full degree is used as a as an estimate for where you're going to find a Groebner basis. The truth is that you can construct systems where the first fault degree is larger than the solvent degree, or is lower than the solvent degree. And so it's not a very good measure, really, of the solvent degree in general. But in many cases, it works. And sometimes it's the best you can find. Given a system, you can predict a non-trivial CCG at some degree, and therefore you have a bound on the first fault degree. Sometimes that's the best you can aim for. Okay, any questions there? All right. There's more recently a notion of last fault degree, which is quite interesting. It's in a sense a better measure of the solvent degree than the first fault degree for non-homogeneous systems. It captures very well the idea of the saturated Macaulay matrix or this what we do for non-homogeneous system, which is trying to get as much polynomials at a certain degree before moving on, get the drops in degree and keep multiplying them. This notion of last fault degree captures this idea very well. I consider it is beyond the scope of this course, so I'm not going to go into details on the last fault degree, but it's an interesting notion. It's very recent, and it's quite useful to go into this and take a look if you're interested. So and now for the last part, if there are there questions before I move on? All right. So if there are no more questions, for the last part, I'm going to talk about matrix reduction algorithms. Just at a very general level, because so at the end, you end up with a large matrix anyways, and you have to try to do Gaussian elimination on that matrix, and so that's also an important issue on this topic, how to do these matrix reductions. All right, and so for small systems, we can use fast matrix reduction algorithms such as Strassen. Strassen is not the best, but it works very well. It's very practical. It is relatively easy to implement. The constants are small. It's a very good standard algorithm to do Gaussian elimination efficiently. And the exponent is a bit below 3. It's 2.81. So that in this case, the complexity of the whole process is given by, or is bounded by, n plus d choose n to the 2.81. So this n plus d choose n, this binomial coefficient is the number of monomials up to degree capital D. So here, capital D is the degree up to which you have to go. Let's say the solving degree. If you know the solving degree, you know that the complexity is bounded by this quantity here. So now we have gone through the whole circle. We know we can solve systems of polynomial equations using linear algebra. We need to do it on a very large matrix. We need to, the size of that matrix depends on the degree at which you have to go. But suppose we know what degree you have to go up to, then we know how many monomials there are, and then the complexity, the bottleneck is doing Gaussian elimination on that matrix. And we have good algorithms to do that, like a Strassen. And then the complexity of the whole process will be bounded by this, will be dominated by this step. However, for larger systems, a sparse linear algebra algorithm is required. So if the system is too large, you cannot even store it as a dense matrix to be able to do Strassen. So you definitely need to rely on a sparse linear algebra algorithm. And here I give an example of one in this citation, L10, where they design a sparse linear algebra technique and sparse linear algebra algorithm specifically for the structure of the F4 algorithm. So these matrices have a very particular structure. Maybe I can show you one, just as an example. Because you are taking polynomials and you're multiplying them by variables, they get very sparse very quickly. So here at the bottom, we have degree 2 dense polynomials. And then you expand them, multiply them by variables. And then you expand them, multiply them by degree 2 monomials. Then you expand them to degree. And every time you expand, the number of coefficients in each row doesn't change, but the number of monomials in the ring does increase. So they get sparser and sparser as you go up in degree. And therefore, we can design specific linear algebra to solve these kind of matrices. And that's so a big part of a quick algorithm to solve, to find Groebner basis and to solve systems polynomials is to take advantage of that structure and do it very efficiently, avoid as possible reductions to 0 and so on. Now, the complexity of those algorithms depends on the sparsity of the matrix, depends on how high you go in degree. So I'm not going to give a precise number for this. It depends really on the sparsity. So it's not so easy to write a closed form of that, right? Okay, before this, I want to mention something else that is important. So I said that sometimes it's even hard to store the matrix. So in cryptography, we're talking about very, very huge matrices that you have to solve. And the memory complexity is large, but even there's a big issue because just so the time complexity is since the matrix is so big, you cannot really store it locally. You need to store it to store the matrix remotely. You need to store it distributed, and the assumption that you can access an entry in no time is not true. There's a cost on just accessing the memory. So the cost of memory access when the matrix is very, very large starts to dominate the whole complexity of the process. So this is also an area of research that is ongoing because nobody has, I mean, there's few research that has really looked into this. And it's much more important than we thought. Okay, there are also hybrid algorithms for such as crossbreed that can be faster for small fields. So when the field is very small, like GF2 or GF3 or something, you can try to guess some of the variables. And guess and solve until you get a solution. So let's say you guess 10 variables and then you solve for the other ones. And if we are in GF2, then you have to do, and you're guessing 10 variables, you have to do this 2 to the 10 times. So you solve 2 to the 10 times, you try to solve the system. Sometimes this is useful, and the crossbreed algorithm is even smarter. It somehow breaks the problem of solving the system into 2 matrix problems. It guesses perfect. It finds a subsystem that is easier to solve. So there are these hybrid ways to do it that are quite useful. There are also quantum algorithms. So there are versions of these kinds of algorithms for quantum computers. Here is one. What they do is they use Groebner to improve the search for a solution for the guessing. So in these hybrid algorithms, you can do the guessing a little bit faster using Groebner. Of course, if we ever have quantum computers, but yes, there are quantum versions of these algorithms. Okay, for those interested in this problem and the way and the algorithms to do it, there's something called the Fukuoka MQ challenge. And in the Fukuoka MQ challenge, what we find is so there are a number of challenge systems to be solved, and you can look here for the best algorithms to solve, and also for challenges to try to solve large systems over finite fields. This has been set up by the cryptographic community to promote that people do research on this. So there are different sorts of challenges for different finite fields and different sizes. And there's here the Hall of Fame. So, for example, here we have Antoine Jus on the first place. For these type 1 systems, they were able to solve for 74 variables, and they give some information on what kind of system what kind of algorithm they used, and what system they used to solve it. Right. So here we see that they use a hybrid version of Excel algorithm. So, as I said, these hybrid versions tend to be faster when you have a finite field, and sometimes the Excel is better because it's simpler, even though it has these zero reductions, but it works very well. So before I finish, I like So I like to do a little bit of advertisement for the kind of research that I'm working on. So we have been working on this mean rank problem. The mean rank problem is the problem that given K matrices over a finite field, you have to find a linear combination of them of rank less or equal to a given value R. This is very relevant for cryptography. It has shown to break. If you can reduce many problems to this mean rank problem. And in the post-quantum niche competition, many schemes have been broken using a reduction to the mean rank problem, including Guy, Gems, Rainbow Lake, Locker, and Rollo. Some of these are multivariate schemes. The other ones are based on coding theory, where the metric is the rank metric. And here in this paper, we were able to break some of the rank versions, and part of what we did was we developed a new way to describe this problem as a system of polynomial equations, and we developed an algorithm to solve that using a system of polynomial equations. It's called the support minors modeling. And then in a way, we solved the system without computing the Groebner basis. And this is also interesting because I've talked for 4 days now about computing the Groebner basis, but it turns out that in some cases, you don't need the full Groebner basis. You are looking for just one part of that Groebner basis that gives you the solution. In our case, we're just looking for the x sub i's. And if you get linear equations on those x sub i's, you're good. That's all you need. The system we construct has many other variables, but sometimes, but we don't need to solve for those. We just need to solve for these ones. And that's often the case. You can, so there are algorithms in which there are situations in which you can look at part of the ideal and look for useful equations in that part of the ideal. That's the case, for example, for bilinear systems. In this second paper, this one here, improving support minors, rank attacks applications to James and Rainbow, we got an even better attack on gems, and we set up and we discussed the complexity of breaking Rainbow. In this case, one of the interesting things is that we discussed the problem of memory access on these huge matrices. For this particular system, we were able to use the structure of the system that we know of the matrix. Because we know the structure of the system, we know the structure of the matrix, and we were able to do most of the computation locally. So even though the matrix must be stored distributed, because of the structure of this system, we were able to make the computations locally. And in that way, show that it was not so expensive to access memory for this particular case. But it's, in general, a very open question. How do you store these large matrices? How do you access the memory? Right. Right. At the end of the slides, we have the references. There are 3 sets of slides. I also put at the end these additional references that I use to prepare the lectures in this series. And with that, I'd like to thank everybody. And for the audience, for the people who connected, and I'd like to thank also SIMPA for making this possible, and ICTP for helping us with the space for all these things to work on time. It's been a great, they've done an excellent job. The production is very good. So thanks everybody. And I'm open to answer questions. Yes, there will be. So we don't have the link yet, but this will be uploaded to the SIMPA YouTube channel, and you can look it up there. Right. If there are no further questions, then have a good day, and thanks for listening.